Hello everyone, thank you for joining me. So today I'd like to begin a new video series which I'm going to entitle Understanding OSPF and GNS3. Now to do this I had to modify some things. So first and foremost I had to completely flush out the EIGRP topology that we had in the previous video. So these are 4 bare bone routers that we're working with from scratch, okay? So like always, we need to prime the links to be able to support OSPF. So I've configured the interfaces as follows. So as you can see, Edge 1 has an interface 0, 0, and 0, 1, which is right here. Interface 0, 0, and 0, 1 on Acme Edge 2, 0, 1, and 0, 0, and 0, 0, and 0, 1. And this is interface 0, 2 right here. Okay. This is the configuration. So they're point-to-point links. So you can see how Acme Edge 1 is .1 and Acme Edge 2 is .2. And this pattern essentially follows through on all the interfaces downstream. Okay. I've also accompanied with the appropriate IP version 6 address on the interfaces because we will be talking about OSPF version 3 in this video series as well. So what I'd like to do is I'd like to go ahead and apply the configuration and then come back. All right. Okay guys, so I've completed the IP version 4 and IP version 6 configurations on the appropriate routers, and I've laid the foundation to then be able to then apply the OSPF process, which we will be doing together. But before we actually do that, I just want to go over one very important point, which I think is a point that needs to be emphasized, okay? And that is that every single interior gateway routing protocol, okay, has an objective. And its objective is to create a routing domain, okay, that prefixes that can then be announced into. Okay, so when prefixes are announced into this routing domain, essentially what's happening is that the routers making these announcements are just telling the rest of the network how to reach certain destination networks. So when you're looking at my configuration, okay, you're going to see that the first step is to create this particular adjacencies. Okay, and these adjacencies are important because you're priming the network to then allow these routers to announce prefixes that reside beneath it. And these announcements are used to tell the rest of the routers participating in the routing domain how to reach these destination networks. And we're going to learn how OSPF accomplishes this task. But for all intents and purposes, router 1 will be doing the same thing. He will be announcing into this OSPF routing domain how to reach the default route or how to reach the internet. Okay, the stub area, this stub network, will also be announcing out these prefixes, which in turn will then be passed along into this routing domain. See, the routing domain is essentially the repository of all the prefixes of all the destination networks that reside in an autonomous system. And that's exactly what we're trying to achieve. So before we do that, let's go through some OSPF terminology, okay? Now, when we apply the configuration at first, we apply the OSPF configuration, we will have at that point a single area OSPF, okay? Now, a single area OSPF implementations are usually defined as one backbone area, which is area 0. Okay? Area 0 in OSPF is the area to which all prefixes reside no matter what. All prefixes eventually flow back to area 0. It needs to because area 0 is the area that ultimately will lead you to your destination. Okay? You're probably asking yourself, well then why do we create these multiple areas? Right? Well, it all comes back down to convergence. See, the general rule is that you do not want to have more than 50 routers in a particular area. The more routers you have in an area, the more adjacencies you have in the area, the more OSPF link state packets and updates, and generally it becomes unscalable over time. So OSPF has the ability, okay, to segment your single area into sub-routing domains to limit the amount of OSPF packets that flow within it for a much more interior gateway protocol strategy. Okay, so moving forward, there is some terminology that we need to be accustomed to. So router 3, because it has an interface in area 1 and 2 interfaces in area 0, this is called an area border router, an ABR. Router 1, for example, is not connected to another area. However, it is the exit point out towards the internet. It is the edge of our network, okay? And it would be considered a autonomous system border router. Okay, the name autonomous system keeps coming back in the discussion. It is the router where traffic can exit the autonomous system that we are trying to create. Okay, so having said that, let's go ahead and show you my configuration. All right, so here is my configuration. So this is the configuration that we'll be using to actually build the OSPF routing domain backbone area 0. So to begin that, we have to start off with router OSPF 1, okay, where 1 is the process ID. All right, we define a router ID, which will be used to source the update packets when the adjacency has begun. And we want to pay close attention to the network command, okay? The network command, what it's stating is basically stating if you have any interfaces, okay, that pertain to this subnet /30, it is allowed to have an adjacency in area 0, meaning that Acme Edge 1 is defined as 10.100.1.1 and Acme Edge 2 is defined as 10.100.100.2. This is a /30. This network command defines this relationship. The same thing goes for Acme Edge 2. This command is identical. They match, coincidentally, for the very same reasons. Acme Edge 2 has an interface that pertains to the subnet 10.100.100/30, and so does Acme Edge 1. So therefore, they will be able to create an adjacency. Now, this rule is replicated throughout all the other routers, and by doing so, we have now created our OSPF routing domain. Now, I've already applied this configuration, and by applying this configuration, I also did a packet capture on this adjacency here, which I would like to concentrate on, and by doing so, I'd like to take a look at what I have to show you here. So, when an adjacency comes up, the OSPF routers that are creating this adjacency have to go through 7 operational states, okay? They go from the down state to the init state, then they go to the two-way state, and then what happens is they transition into the X-start state, the exchange state, and the loading state. So the down, the init, and the two-way is for neighbor establishments. The other 3 states are for OSPF database definitions. As the 2 routers are going through these states, okay, they are exchanging these packets: the hello packet, the database descriptor packet, the link state update packet, and the link state acknowledgement packet. Okay? Then what happens is the router goes into a full state. And we can see that by looking at the neighborships with the show IP OSPF neighbor. Now, I want to concentrate on Acme Edge 1 and Acme Edge 2. Okay? I want to concentrate on these. Now, it's really nice to see that they're in a full state, but we have a little bit of a problem. Because even though they're in a full state, what's happened is that they are electing a designated router and they're also electing a backup designated router, which is this guy right here. Now, the reason for that is because OSPF has embedded in the process the ability to interpret which interface it's connected to. So, for example, we have the OSPF adjacency, okay, configured on gigabit Ethernet, right? So if I do show IP, OSPF interface, brief, okay, we can see that it's been configured on a gigabit Ethernet interface. OSPF recognizes the gigabit Ethernet interface as a LAN interface, so it interprets it as a broadcast network. And when it interprets it as a broadcast network, it is recognizing it and says we need to create a designated router and a backup designated router, even though visually it's a point-to-point /30. Okay, this is a really big problem because as your network grows, right, as your network grows, the more packets or link state packets are being sent on these links that are unnecessary. So for example, if I go to show IP OSPF database, I can see that these are link state 1, so LSA 1 type packets and LSA 2 type packets. LSA 2 type packets only exist when there is a backup designated router and a designated router that has been elected on a broadcast medium. But again, this is a point-to-point link. So there is some tweaking that we need to do. Okay? Okay? Now, to be able to fix this, what we do is we go config T, interface gigabit Ethernet 0, and we do IP OSPF network point-to-point. And we do that for all of them. Okay? Config T, interface gigabit 0, IP OSPF network point-to-point. Bear with me. Okay, so as you can see now, when I do an OSPF neighbor command, there is no border gateway, designated router or backup designated router elected. Okay, and you can see that, which is a very good thing because now we have just optimized the OSPF performance. Okay, so we have one more here. It is not config T interface gigabit Ethernet 0, 1 IP OSPF network type. Okay. All right, that came up really quickly actually. Okay, so and that's what we want, right? There you go. So now we have just eliminated that. But the best part is take a look at this. If I do show IP OSPF database, I have just eliminated that redundant LSA type 2 packet that was flooding my OSPF database, which is important because as your network scales, you want your OSPF link state database to be as small as possible so then you can achieve the faster convergence. Okay, so that's very important. Okay, so let's go ahead and take a look at the routing table. If I do a show IP route OSPF, I can see some interesting information. So this O for OSPF means that the route or the prefix 10.100.100.0, this subnet, has been learned via an LSA type 1 update. Okay, so this is an LSA type 1 update. is identified as an O with an administrative distance of 110 and a cost of 2. But how does it actually come up with a cost of 2? Well, OSPF embedded into the actual routing protocol also has the ability to calculate its own metric. And how does OSPF accomplish this? It accomplishes it by taking the reference bandwidth, which is 10 to the 8, or 100 million bits per second, and dividing it by the interface bandwidth. Okay? So this makes it very difficult for OSPF to actually accommodate interfaces that are higher than 100 megabits per second. So to alleviate that constraint, what we do is we go under the router config t router OSPF 1 command, and we type in auto cost reference bandwidth. And what this does is it changes the value of the numerator. Okay? And by changing the numerator in the calculation, you now leave room for OSPF to calculate interfaces that are higher than 100 megabits per second. Now this needs to be accomplished on all the routers. So why don't we just do that? Okay. Okay. Now after we've accomplished this task, we're going to clear the process on all of them. Actually, let's do it over here. Okay. Now if I go back to show IP OSPF, show IP route OSPF, you can see that the cost has now changed to 20. And the reason is because under the OSPF process, we have just changed the numerator to which OSPF uses to calculate the cost of the bandwidth. Okay? Okay. Another things I'd like to mention to you is that if I do a show IP OSPF interface command, some of the configurations that need to be noted here are the time intervals. So IGPs, like interior gateway protocols, all have a hello timer that basically basically means I'm going to send out a hello out this interface. I'm going to wait 10 seconds. Okay. And I'm going to wait 10 seconds for a response before retransmitting 5 times. Okay, and if I don't get a response back after 40 seconds, I'm going to terminate the adjacency. Okay, so these values can actually be modified under the interface. And what's important here is you can do IP OSPF hello interval, and then you can modify the value to, let's say, 20 seconds. You can modify the dead interval to be, let's say, 60 seconds. And most importantly, you can also modify the cost. See, up until this point, we were allowing OSPF to determine the cost of an interface organically on its own by using the bandwidth of the interface and dividing it by the reference bandwidth. But best practice is for the administrator to have full complete control over the traffic patterns in their network, and you do that by statically assigning the IP OSPF cost command with a value of, let's just say, 6 for a 1 gigabit interface, or you say 1 for a 10 gigabit Ethernet interface. And it's a study that needs to go on when you're building out your OSPF routing domain. Okay, so if you like this video, please like, subscribe, and share, and thank you so much for being with me today.